Hey everybody, Dr. A here, and in this video we're going to be providing some background information on a new topic called strain, okay? So what is strain? Strain is a measure of deformation in a body. Now, the next question becomes, what is deformation? Well, deformation is a change in a body's shape or size. So in general, deformation is not going to be uniform throughout a body's volume. Let's think about that. Let's say that you have some kind of body. Maybe that body is a machine or a structure or a table, and you apply a load to it, and it changes shape or size due to the applied load. Is that change in shape or size going to be uniform throughout the body's volume? No, not at all. Not at all. You're going to have more change in shape on one end versus the other end or part of that particular body. Okay? So when we talk about strain, there are two types of strain that are going to be of importance to us. The first is called normal strain, and the second is called shear strain. Now, the letter or the label we use for normal strain is the Greek letter epsilon. It's a lowercase epsilon. And the labeling for shear strain is the Greek letter gamma. All right. And so we're going to give you the definitions of each one of these, and I'm going to draw some figures and kind of draw a little bit more on this page for us to help us understand what each one of these means. Okay. So let's start with normal strain, which we label epsilon. Normal strain is the change in length of a line segment. Now, that change in length of a line segment, we're going to call that delta, okay? Delta, or the change in length of a line segment, is an example of this word deformation that we talked about a few minutes ago. So we take the change in length of the line segment, delta, and we divide it by the original length of the line segment, L naught. And that is what we define as normal strain. So mathematically, what is this going to look like? We're going to say epsilon is delta over L naught. Okay? Now, we said delta, this little delta here, Greek letter delta, is the change in length of a line segment. So I'm going to say where delta equals the deformed length of a line segment, which we're going to call L prime, minus L naught, okay? And so, again, L prime is going to be known as the deformed length of line segment. So we can rewrite this as epsilon equals L prime minus L naught divided by L naught, okay? Now let's talk about what this is going to look like graphically, okay? Let's say that we have this line segment. I'm going to change colors here. Let's say we have this line segment, and we're going to call it AB, okay? And let's say this line segment is part of a body, okay? So let's just say that, you know, this kind of blob right here that I just drew around line AB is represents a bigger system. Maybe it's a structure, maybe it's a building, maybe it's a machine, maybe it's a table, whatever, okay? And so we're going to call this the undeformed body, okay? Now, what is the original length of this line segment? Well, that's going to be that value of L naught, all right? Now, let's say we apply loads to this body, okay? We apply loads to this body, and let's say that the body deforms into another shape. We're going to call this the deformed body. Okay, now what is that line segment going to look like now? Let's say that we had some loads here, acting like this. And now that the body is deformed, what shape is that line segment going to be? Well, it's going to be some other shape now, okay? So maybe B is going to be at a new place called B prime, and let's say A is going to be at a new place called A prime, and this line segment is now a different shape. All right. So what do we look at now? Well, the length of that line segment now is going to be L prime, okay? So that's what we mean by the deformed length of the line segment. Now, when we consider very small line segments, we're not going to be considering the curvature of the change of these line segments. So let's make a note of that here, okay? I'm going to make a little asterisk here. For small line segments, we do not consider the curvature of L prime, okay? So we see that L prime is some kind of new length, all right? So here's my question to you. When we are talking about normal strain, okay, this goes hand in hand with axial loading, all right? So when L prime is bigger than L naught, what do we experience here? So let's make a note here. When L prime is bigger than L naught, that means that you have a stretching or tensile effect, okay? So you're going to have positive strain and you're going to have stretching, okay? What happens when L prime is less than L naught? You're going to have a negative strain, right? So that strain value will be negative, and you're going to have compression in that line segment, okay? So that's the idea of average normal strain. Now, could we look at a differential version of this? Yeah, absolutely, absolutely. So what would the differential version of this be? So I'm going to write this over here. Okay? What would the differential version of this be? So what we could say is epsilon is also going to be equal to dL prime minus dL naught divided by dL naught, okay? So this right here is the differential version of this earlier version of the formula that we wrote down, okay? Now, when would we need the differential version? Well, if we have a nonlinear normal strain, so let's say that the strain is varying in some kind of nonlinear way, or let's say that the strain is varying based on a function, a deformation function, we could model that using the differential version of this equation, and really that just comes from putting some d's in front of that. Now, if you want to look into the background of this, really what you're doing is you're applying the limit of the difference quotient to this formula right here. If you remember from Calculus 1, the limit of the difference quotient gives you a derivative, and so that's how we come up with this version of the formula, okay? So this is our background of normal strain. What about shear strain, okay? We said shear strain is another type of strain that we're interested. So let's move on down. Shear strain is the change in an angle between two line segments, and it is measured in radians, okay? So what's the letter we use for shear strain? We use gamma for shear strain, all right? So let's say that we have a body here, okay? And let's say that we have two line segments. Let's say that we have line segment AB, and let's say that we have line segment AC, okay? And let's say that there's an angle in between them, and let's call that theta, okay? And so let's say theta is the original angle between segments AB and AC, and this is the undeformed body. Now let's say that we apply some loads and this thing becomes deformed, okay? And And remember, this body could represent anything. It could be a bridge, it could be a building, it could be a machine, anything, all right? So we apply loads, and these line segments deform, okay? And so let's say they deform to a B prime location and an A prime location and a C prime location. Now, there's going to be a new angle between these line segments, and we're going to call that theta prime, okay? And this is the deformed body. All right, so what is theta prime? Theta prime here is the new or deformed angle between segments A prime, B prime, and A prime, C prime, okay? And so what is that shear strain? So the shear strain is going to be the change in angle between the original angle and the new angle. So the change in angle between theta and theta prime. So we're going to write this as gamma equals theta minus theta prime, okay? Now, this is what we typically see in a lot of mechanics of materials textbooks. Some people might express this as theta prime minus theta, but just to be consistent with what we see in a lot of textbooks, I'm going to stick with the original angle minus the deformed angle. So what does this mean for us? We're going to say if theta is bigger than theta prime, then we're going to have a positive shear strain. If theta is smaller than theta prime, we're going to have a negative shear strain. So that would mean that your new angle is bigger than your original angle, so you have kind of an expanse of the angle, okay? Versus if your new angle is smaller than your original angle, you have kind of a compression effect or a condensing at that angle, at that spot, okay? So if you found this video helpful, please hit like and subscribe and be on the lookout for some numerical examples of us illustrating both normal strain and shear strain. Thanks for watching.